to my fellow Europeans. Good morning to those who join us from the Americas. We always have people joining us from there. And a late good evening or a very early good morning for those who join us from Asia. This is the International Space Science Institute's Game Changers seminar series, where in this quarter, we look at ideas and findings about the solar system, the universe, and our terrestrial environment. And today we have a talk on planet formation and evolution, key processes to understand the diversity of planetary systems. And our speaker today is Alessandro Morbidelli, also known as Morbi. Next week, we will look at the merger history of the Milky Way, what Gaia revealed with Eva Krebel from the Center for Astronomy of the Heidelberg University. If you want to stay abreast of the seminar and other ISI activities, consider subscribing to our newsletter. You can do that at the bottom of any of our web pages. Introducing our speaker, Morbi is a researcher in astronomy at the Observatoire de la Côte d'Azur in Nice, France, specializing in celestial mechanics, the theory of Hamiltonian systems, and the formation of planetary systems. And I think one can say that he's truly one of the pioneers of our present understanding and present modeling of the solar system first, but also of planetary systems in general. He's an associate member of the French Academy of Science and of the Royal Academy of Belgium. And he received the Prix Janssen of the Société Astronomique de France in 2018 and the CNRS Silver Medal in 2019. I'm very thankful to have him here today and explain us how solar system formation and planetary formation works. Morbi, the floor is yours.
Thank you very much, Tilman. I'm grateful for the invitation. And so let's go. So I try to share the screen. Is this okay?
This is okay.
It works. Okay. So as the title says, well, first of all, good morning or good afternoon to everybody. So as the title says, I would like to discuss planet formation, the formation of the solar system in the broad context of general planet formation. And of course, this calls to discuss the diversity that we observe in planetary systems. So up to the discovery of the first extrasolar planets, we only, of course, knew the solar system as a unique example of a planetary system. And I think everybody, even if many people say, no, indeed, everybody thought that every planetary system should have been similar to ours. And our solar system is clearly not random, and it has a structure. In the inner part of the solar system, we have the terrestrial planets, which are relatively small. You know, the Earth is the biggest of them, which are rocky, even if some planets have an atmosphere. In terms of mass, that's negligible. And further away, we have the realm of the giant planets, which are much more massive, from 300 Earth masses for Jupiter to 15, 17 for Uranus and Neptune, but also have a different composition. They have a lot of gases, hydrogen and helium, the same gases of the protosolar nebula and the sun itself. And these gases make the majority of the planet of mass for Jupiter and Saturn, and still a big portion for Uranus and Neptune. So really two distinct categories of planets, and there is an asteroid belt, a sort of boundary or frontier between these two populations. And then we have another planetesimal population beyond the planets, where planets could not form. In addition, all planets have orbits which are basically circular, quasi-circular, and almost coplanar. And so we thought that planetary systems would have been quite similar to this, also because all the theories for solar system formation were tailored in order to explain the specific structure of the solar system. So with the logical implication that because physics is universal, all planetary systems should have resulted in something very similar to our own system. And then the discovery of extrasolar planet, of course, changed the game. And this plot now shows the distribution of extrasolar planets discovered up to some date. Here is 2015, but actually the situation has not evolved so much since. And this plot shows each black dot is an extrasolar planet observed in the diagram reporting some major axis, so the distance from the parent star, and planet mass on the y-axis. And the red dots are highlight the planets in our solar system. So there are a few considerations that we need to do. First of all, we have not really discovered the extrasolar planets that are the analogs of our own planets, except Jupiter. But this is an observational bias. Our planets are too small and too far from the sun to be observed around another star with our current technology, with the exception of Jupiter. Jupiter can be seen with radial velocity measurements over a decade or so. And indeed, we have a few extrasolar giant planets overlapping with Jupiter in this plot. But what is astonishing is that of the 4,000 plus planets discovered today, they occupy a region of parameter space where we don't have planets in our solar system. So the planets that we discover around other stars are different from what we have here. And so as you can see, the planets can be grouped in 3 clumps. It's pretty obvious. The first clump is that of the hot Jupiters. These are the easiest planets to discover. So the first planet discovered, of course, was a hot Jupiter. The name is quite obvious. These are planets with a mass of the order of the mass of Jupiter, fraction to a few times, and they are much closer to the parent star. Instead of having a semi-major axis of 5 AU, they have a semi-major axis of 0.05 AU on average, and an orbital period of about 3 days. So they are strongly irradiated by the central star, so that their atmosphere is extremely physically hot, and so the name hot Jupiters. Then we have a sort of gap. There are a few planets, but not so many. And then we have many more giant planets further out, starting at a distance of about 1 astronomical unit and ranging up to 5 astronomical units. So these are called warm Jupiters, sometimes are called cold Jupiters. I like warm Jupiters to highlight that the peak of this distribution is really at 1,2 AU, where we have the terrestrial planets instead, many stars as giant planets. And further beyond Jupiter, where we have problems in discovering planets because the orbital period becomes very long and the perturbation on the central star becomes weak. So planets can only be discovered by direct imaging. And indeed, some planets have been found by direct imaging. They are relatively rare. And so it seems that somehow the population of giant planets starts to decline going beyond Jupiter's distance. How exactly it declines is not so obvious. There has been different attempts to model and debias the observed distribution, and some papers are not completely in agreement, but far enough, planets seem to become more rare. And then there is the third group, which is maybe the one raising most of the interest because of the issues about habitability. These are called the super Earth planets because typically they have a mass between the mass of the Earth and the mass of Uranus and Neptune. Sometimes they're also called mini Neptunes. And you can see some of them are smaller than the Earth, but these are typically planets that orbit stars smaller than the sun. So if we refer to the mass ratio planet to star, they are super Earths in general, even if the Earth mass is, even if their mass is smaller in physical, in absolute quantity than the mass of the Earth. And these planets also tend to orbit much closer to the central star. Again, if there are more distant planets, we don't know, they become non-observable because of observational biases, but there are plenty of super Earths with small orbital radius and small orbital period. And trying to debiasing the observations, hot Jupiters are around 1% of stars, warm Jupiters around 10% of stars, and close-in super Earths are around about half of the stars that in the galaxy. So they are the most numerous, the most abundant planets. So the differences between the extrasolar planets and our own planets are not just in masses and distance from the sun, from the star, but also in terms of orbital shape. As I said before, our planets are basically on circular orbit, and the shape of the orbit is characterized by a parameter called the eccentricity. So a circle has an eccentricity of 0, and the higher is the eccentricity, the more and more elongated is the orbit, as you can see in this sketch. So whereas our planets have eccentricities less than 0.1, with the exception of Mercury, The extrasolar giant planets, this diagram is made for giant planets only, can have very large eccentricities. So here each right triangle is a giant planet depicted in terms of its orbital sine major axis, mean distance from the star, and its eccentricity. And as you can see, the eccentricity distribution is almost flat, ranging from 0 to almost unity. And so this is true up to the tidal circularization limit. So within on this side of this giant curve, tides are too strong, and any planet with no matter what initial eccentricity would be brought down here in the realm of hot Jupiter. So hot Jupiters tend to be rather circular orbit, but this is due to tidal circularization. Further away, where tidal circularization can be neglected, we do really see all kinds of eccentricity. So we have planets, you know, if we take in our solar system, only comets have this kind of eccentricities. And indeed, if we take 60, oh, what is going on? Do you see something?
Yeah.
Okay, no, a window popped out, so it's popped up. Okay, so in our solar system, only comets have these eccentricities. And for instance, if you take the orbit of 67P, the target of the Rosetta mission, the comet is here in this diagram. So at the distance of about 3 AU and an eccentricity of 0.6. And so we have basically around other stars, planets on comet, giant planets on cometary orbit, which was really not expected before the actual discoveries. The super Earths tend to be more circular and more coplanar. In several cases, super Earths appear in systems, whereas giant planets tend to appear isolated. And so here, for instance, I show an example of system of Kepler-62. This is made of 5 super Earths that are here depicted at scale with respect to the sizes of our terrestrial planets. So you see why they're called super Earths, because they are really bigger than the Earth, except this one. And their orbits, typically the entire system is a mini solar system that you can inscribe in the orbit of Venus, and 3 of the 5 planets are even well interior to the orbit of Mercury. Okay, so from the observations, what can we say? So as I said before, observational biases prevent the discovery of systems like ours, but the observations already tell us that about 70% of the stars have planets different from those of the solar system. So have planets that don't exist here. And actually only 1% of solar type stars seem to have a Jupiter on an orbit similar to our own Jupiter. So about 5 AU and relatively circular. I said before, warm Jupiters are around 10% of the stars, but only 10% of the warm Jupiters are far enough and circular enough to look like Jupiter. So Jupiter, as I said, is the only planet of the solar system we could observe elsewhere. The fact that only 1% of the stars have a Jupiter like our own tells us that even if we restrict our the entire characteristics of our solar system to the sole existence of Jupiter, our solar system at most exists around 1% of the stars. And of course, the solar system is much more complicated than the simple Jupiter orbit. So our solar system is rare. We already know that from observation. So our solar system is not typical. And planetary systems are very diverse. The most typical system have super Earths or mini Neptunes close to the central star. So a structure completely different from the one we have here. And so when we work now on planet formation and evolution, of course, the overarching question is to understand the origin of the diversity of planetary systems, given that physics should be universal. So we cannot say, well, some physical processes that occur here don't occur elsewhere. In principle, physical processes should be everywhere the same. And so if we understand this diversity, then the second question is to predict what is the real fraction of planetary systems that are similar to the solar system. And the most interesting is to push this similarity in having a planet like the Earth, so a habitable planet. And if possible, for us theorists, the goal is to try to give an answer to this question before the observers give us actually the real answer. So in order to discuss this origin of the diversity and the likelihood that planetary system may look like us, well, we need to review the basic processes of planet formation and try to understand where the diversity can stem from. So we know that all stars, when they form, are surrounded by a protoplanetary disk. This is generic. What is known already now from ALMA observations is not generic, are the properties of the disk. Some disks are very massive, very extended. Other disks are not very big, just extended a few tenths of an AU. Some have features like rings and gaps. Others are rather continuous, or maybe they have not been resolved. So there can be already quite of a diversity at the level of the protoplanetary disk, but I will not really go into that. So I will consider that more or less all planetary or protoplanetary disks are, for what concerns this discussion, relatively similar. So the disks are made of gas and dust. Dust coagulates because grains can stick together by electrostatic force. And as dust grows, it tends to sediment on the midplane of the disk. But at the same time, it also tends to radially drift towards the central star because the gas rotates around the star more slowly than the grains tend to do, because the gas is supported by the pressure inside the disk. It's a fluid. And so the effective mass of the star that the gas sees is a little bit reduced by this pressure force. And so the gas orbits a little bit more slowly than the grains, so slows down the grains, and then the grains spiral down towards the central star. So this process of coagulation, sedimentation, and migration, where can it bring us? So there has been many laboratory tests about sticking grains together and see how big a grain can grow. And starting from monomers, one can see that monomers stick by electrostatic forces, forming fractal structures. When fractal structures join and gently with small energy, they stick together and form a bigger fractal structure at higher impacted velocity. This fractal structure tends to become more compact and more compact. But then when the energy of collision increases, then the aggregates tends to bounce, or maybe in the collision a big piece is released, and so there is no net growth anymore. And if the energy is even bigger, then the pre-existing aggregates are dispersed. So many of these experiments have been done in Germany, a group of Wurm, for instance, and Bloom. So basically, the results of the experiments show that it's difficult to grow very big grains. Typically, if the monomers are made of silicates, you start to get bouncing and chip off when grains exceed the size of a millimeter. Maybe for icy particles in particular, if you're not too far from the snow line, so what we call warm ice, the sticking properties are better. And so grains can grow bigger, up to centimeter in size, a few centimeters in size. So natural question is whether this is some limitation in our understanding on grain growth or in the way laboratory experiments are done. But we hopefully, luckily, we have meteorites, which are samples of planetesimals that never, so these meteorites are called chondrites, that never heated enough to melt. And so we can still look at these meteorites and see the structure of these planetesimals, what these planetesimals are made of, what is the size of the grains they make these planetesimals. And this is a slice of an ordinary chondrite and show many chondrules, from where the name chondrite comes, some CIs you see here. And all these grains typically have a size, chondrules typically have a size slightly smaller than a millimeter, up to a millimeter, half a millimeter. CIs can be a little bit bigger, some can be up to a centimeters, but they are big. CIs are rare. So indeed, nature shows us that planetesimals have been made of millimeter-sized particles, no bigger than that. So this is not a limitation of theory or of experiments. We really need to understand how all of this, grains grow up to a millimeter, this is understood, and then how we can jump in size from a collection of grains that are a millimeter in size to something big, like an asteroid or a comet or a planetesimal. And the community has remains stuck on this for quite a while. And in the last decade or so, maybe 20 years now, time is passing fast. There has been a revolution in understanding. And the revolution in understanding has been from the precursor work of Jeff Casey, that there are a number of dynamical instabilities that can clump these dust particles, let's call still them dust particles, even if they have a millimeter in size, together. And in particular, two of these instabilities appear to be very promising. One occurs during the sedimentation of the dust on the midplane. It's called the Kelvin, there is an L missing, I'm sorry, Kelvin-Helmholtz instability. And the other one occurs during the radial drift of the dust towards the central star, and it's called the streaming instability. But these are actually two sides of the same medal, if you want. And to illustrate the concept, I will show an animation taken from a work from Anders Johansen on the Kelvin-Helmholtz instability, because I think it's clear. So this shows, the animation shows the density of dust in color. So black is very little density, blue a little bit more, yellow and red even more. In this diagram, where on the vertical axis we have the distance from the midplane. The midplane is here at the center where we have 0. On this axis we have the azimuthal direction around the star. So this is a cut at a given distance from the star. It doesn't matter which distance. So let's see what happens as time goes on. You will see the time going on here, normalized to orbital periods. And first you see that the sedimentation towards the midplane, so the blue band becomes thinner and yellow because the density increases. But then there is this instability that kicks in, so the band of dust does not remain infinitely razor thin. The dust becomes dispersed by this instability and occupies a region, a band around the midplane, which has a given thickness. But this is not a uniform distribution of dust in this band. The turbulence collects the dust in specific turbulent structures. So there are some globules here, those that you see in white, where the density of dust can really be very high. And in the same band, there are regions where basically there is no dust. So the uniform distribution of the dust is broken and the dust clumps. And some of these clumps become dense enough that the self-gravity of the dust becomes dominating. And then a planetesimal, the cloud of dust is bound together and slowly contracts so that all the dust settles on each other to form a compact planetesimal. And different models and simulations have shown that the planetesimals that are formed have a typical size of the order of 100 kilometers, give and take a factor of 2, even if some very big planetesimals, maybe up to 1,000 kilometers, maybe can be done. On the contrary, it's difficult to make small planetesimals by this process, because small planetesimal has a little mass or little gravity. So it's very hard to understand how, a cometary, a kilometer size asteroid or comet can form. The diffusion of the gas tend to disperse the clump before the clump can contract together. So from this, we understand that planetesimals form big, and the small planetesimals that we see, small asteroids, small comets, should rather be collisional debris than primordial planetesimals, because of the inability to form small planetesimals when the mass involved is too low. Okay, so once we have planetesimals, we still have to build planets. Of course, planets are much bigger. And how can we do that? So we need to go from planetesimals to planets. And there are two processes that are operational. One is that planetesimals can collide with each other, and because they are sizable, 100 kilometers or so, they have a non-negligible gravity. So if they collide gently enough, their common gravity puts them together. And this process leads to formation of protoplanets by the oligarchic growth process, followed by the runaway growth process, followed by the oligarchic growth process. And it has been shown to be able to form sizable planets of a mass of Mars, or maybe even a mass of the Earth. It may be a little bit difficult to form a really multi-Earth mass objects, such as the objects expected to act as seed to form the giant planets, but this is still debated in the literature. The other process has been discovered more recently, 10 years ago, is that once the protoplanets become big enough, say more massive than the moon, they can also start to accrete individual dust particles as the dust particle drift in the disk because of gas friction. And this process has been called pebble accretion. It's a new paradigm of accretion. And so it's interesting to compare the two. So pebble accretion has some advantages over planetesimal accretion, because if a planet grows by accreting planetesimals, say it can accrete all the planetesimals in its neighborhood, but once it has emptied its neighborhood, because planetesimals are big, so they don't move radially in the disk, they are not affected by gas drag significantly, the planet starves, right? It has accreted all the planets in its vicinity, cannot accrete the planetesimals which are too far away. Pebble accretion doesn't have that problem because dust drifts in the disk. So even if a planet accretes all the dust in its neighborhood, new dust will come in. So there is no isolation, okay, until the planet becomes really very massive, as we will see later. The second advantage is that the cross-section to accrete a dust particle is bigger than that to accrete another planetesimal. This is shown in this nice animation made by Michiel Lambrecht, showing a planetesimal at the center that tries to accrete, and there are two particles coming in with the same impact parameter, same impact velocity. One is another planetesimal, and it's the one in black, leading to the black trajectory, and the other one is a dust particle leading to the red trajectory. And you immediately see the difference, right? The planetesimal comes in, its trajectory is deflected by the gravity of the accreting body, but because the impact parameter is a little bit too big, there is a miss, and the planetesimal flies away. There is no accretion, no growth. But the dust particle, even if it comes in with the same impact parameter, same velocity, as soon as it's deflected, its gas drag goes to the roof. And because of this enhanced gas drag, then the red particle has a different trajectory than the planetesimals and spirals in until it lands on the accreting body. So the body accretes the dust particle, does not accrete the planetesimal, which means that the gravitational cross-section for accretion is bigger for pebbles than for planetesimals. So you combine the two things together and you attempted to conclude that pebble accretion is more effective than planetesimal accretion. But attention, because community can be very excited by new ideas, but there are some conditions which need to be fulfilled. First, the accreting body has to be relatively big, bigger than the lunar mass. And to grow up to there, you need collisions, planetesimal collisions, most likely. And then you need to have enough pebbles around to have an important accretion. And pebbles drift, and disks tend to become empty, right? In particular, if the disks are small, the grains drift radially and can all go towards the star, and then a planet cannot grow very massive simply because there are not many pebbles to accrete. And so one has to analyze case by case how far pebble accretion can grow a body, and whether planetesimal collisions or pebble accretion becomes the dominant growth mechanism for a planet. From the qualitative point of view, it's striking, this dichotomy that I showed before in the solar system, that we have small planets closer in and big planets further out. And in particular, if we, at the core of these giant planets, there should have been a solid planet of about 10 Earth masses, something that formed quickly before the gas went away, so that its 10 Earth mass core could accrete the gas from the disk. Whereas we know the Earth took a lot of time to form, and most likely at the end of the lifetime of the protoplanetary disk, it was only probably an embryo about the mass of Mars. Oops. So the mass contrast is actually very big, right? Within the lifetime of the protoplanetary disk, the planetary growth process was able to make 10 Earth mass planets in the outer disk and only Mars mass embryos in the inner disk. And why? How? Because the orbital periods are shorter closer in. So in principle, everything should happen faster because the orbital period is the clock. And so if you start from a smooth nebula, which has, say, the same amount of mass in every AU wide ring, it's almost impossible to understand why giant planets formed further out and small planets closer in. So either the initial mass distribution of planetesimal was completely uneven with a lot of mass in the outer disk and just a few planetesimal forming, just a few Earth masses of planetesimal forming in the inner disk, or something else must explain this dichotomy. So pebble accretion can potentially explain this dichotomy really simply, because pebble accretion is very sensitive on the size of the pebbles. And so in the disk, as you all know, I guess, there is a gradient in temperature. The disk is hot, relatively close to the star, and cold further out. So there is a distance that we call the snow line, within which only silicates or refractory materials are solids, and water is in the form of vapor, for instance, and beyond which water condenses, and we also have ices. And as I said before, ice is thicker than silicates, so we can imagine that the grains that are formed beyond the snow line are bigger than those that are formed inside of the snow line. Inside of the snow line, we said, as I said before, there is this bouncing barrier which prevents grains to grow bigger than a millimeter. Beyond the snow line, ice can in principle form a gluey matrix, sticky matrix, and so we can envision that maybe the grains have a sizes of a few centimeters, comprising silicate grains, which are small, embedded in this icy matrix. And when these pebbles drift, of course, they approach the snow line, and when they pass inward of the snow line, the ice evaporates by definition of snow line, so we lose about half of the mass, and possibly these silicate grains are released by the evaporation of the matrix. So we have a contrast in size of the pebbles that protoplanets can accrete. The pebbles are relatively big beyond the snow line and much smaller within the snow line. And pebble accretion is very sensitive to the pebble size. So for instance, if we take two protoplanets, say half the size of the moon, one just inside of the snow line in green and the other just outside of the snow line in red, so to have all things equal apart from the size of the grains that they can accrete, what the pebble accretion formulas show is that the outer planet, because it sees bigger pebbles, grows much more quickly than the inner planet that sees much smaller pebbles. And so by the time the outer planet reaches 20 Earth masses, the inner planet reaches just the mass of Mars. And the simulation here is stopped at 20 Earth masses, because at 20 Earth masses, a new phenomenon appears, which is dynamical barrier to dust drift. What the hydrodynamical simulation show is that once a planet starts to have a mass of tens of Earth masses, it starts to carve a gap in the gas along its orbit. So this diagram here is the result of hydrodynamical simulation, shows a planet embedded in a disk. This is the radial distance from the star. This is the azimuthal coordinate. And the colors show the density of gas, and blue means little gas and red means a lot of gas, sorry. And so as you can see, the planet is here, launches a spiral density in the disk, opens a gap along its orbit where there is little gas, and gas piles up at the edges of the gap. So as a result of this sculpting of the gas distribution in the disk, the velocity map of the orbital velocity of the gas changes. And this is illustrated in this right diagram. So this shows, as a function of the heliocentric distance from the star, so the same coordinate is here, the orbital velocity of the gas normalized to the Keplerian speed, which is the speed at which the dust grains want to orbit. And as you can see, far from the planet, here inside and here outside, the disk is sub-Keplerian. Its orbital velocity is less than the Keplerian velocity. This is why the gas exerts a drag that makes particles drift towards the star. But close to the planet, as you can see, the velocity of the gas changes a lot. And in particular here, in correspondence of this accumulation of gas at the edge of the gap, the velocity of the gas can become super Keplerian. And that means that the gas is orbiting faster than the dust. It's not dragging the dust, it's pushing the dust out. So what does this mean? Imagine you have a dust particle here. It's in the outer disk. It sees a subcaplarian disk that slows the particle down, so the particle drifts in. But when it comes here, imagine we have a 50 Earth mass planet where the gas turns from subcapillarian to supercapillarian, the drag ends. And if the particles entered below, it would be pushed out. Okay, so the particles come in and stick here and don't continue their drift towards the star. This is the giant planet barrier. And so at 20 Earth masses, you see the gas starts to be super Keplerian, so this barrier becomes effective above 20 Earth masses. So Jupiter, of course, accreted all its mass within the protoplanetary disk. And so Jupiter eventually exceeded 20, 30, 50, 100 Earth masses. So clearly this happened in the solar system. And the growth of Jupiter is indeed the key to understand the separation of the material, of the solid material in the solar system in two distinct reservoirs without mixing. And we do see that in meteorites. It's a very important paper by Kruger et al. In PNAS in 2017. The solid material that we see in inner solar system planetesimals and the solid material that we see in outer solar system planetesimals are distinct from the isotopical point of view, which means that the outer disk material could not drift into the inner solar system in large quantities. And we think that this is due because Jupiter at some point became big enough to block it all. And of course, the lack of material penetrating into the inner solar system limits the capability of inner planets to grow by pebble accretion because there are no more pebbles coming in. The dust in the inner disk goes towards the star, and the dust from the outer disk is stopped by Jupiter. So our terrestrial planets are unlikely to have grown by pebble accretion. And I would say luckily, because if an Earth had grown by pebble accretion, it would have become an Earth mass in the disk of gas and would have migrated. So it would not be at 1 AU today, it would be much closer to the sun, and we will not be here to talk about it. So we think that at the moment Jupiter appeared, the solar system was divided in two. The dust accumulated outside of the giant planet orbit, and the inner solar system became quite clear of dust, and so nothing could grow by pebble accretion anymore, and growth could continue only by planetesimal collisions. And we do see systems like this in extrasolar planetary disks. These are called transition disks. So disks that are very rich in dust beyond some limit and very poor in dust, although there is gas because we see stellar accretion or the accretion of gas from the star inside some limit. Of course, because of observational limits, these cavities that we observe, the transition disks, are much bigger than 5 AU, but this is only probably an observational bias. So up to this point, everything I described looks pretty standard, pretty general, right? So grains should be big beyond the snow line, small within the snow line. So planets should grow rather big by pebble accretion beyond the snow line, could only grow more slowly within the snow line, and eventually maybe be blocked. Their growth by pebble accretion be blocked if one of the outer planets exceeds the pebble isolation mass. So where is the diversity coming in? Well, there is an additional process that I've not discussed yet, which is migration. Once a planet becomes massive enough, it starts to perturb the disk, and in reaction, it receives forces from the disk that force the planet to drift towards the central star. And migration is also a generic process. Okay, so these small planets in the inner disk, because they remain small, they don't migrate significantly, but the large planets that should form beyond the snow line by pebble accretion should all tend to migrate in. And of course, by migrating in, they destroy this nice order of small rocky planets inside and large icy planets outside. And this introduces a lot of chaos, and chaos opens the door to the development of diversity, because when you have a chaotic process, then little differences in the initial conditions or little differences in the environment can lead to large differences in the outcome. So I would like to illustrate this point with a few examples. I don't pretend to be exhaustive in what I'm showing you. I will just show you 3 examples of how different planetary systems can become depending on little difference at the beginning. So let's take the nominal case. So we have a star, we have a protoplanetary disk. So this yellow rectangle shows that there is gas in the system, and there is a snow line somewhere. So inside of the snow line, the planets form relatively small, and outside of this snow line, they form bigger because pebble accretion is much more efficient. So what happens in general? That planets migrate. So let's neglect these little planets here because they are small, they don't migrate much, and they don't influence the big ones. So let's remove them from the simulation. And let's see a simulation of what happens when migration kicks in. So we see the evolution of these planets in terms of distance from the central star, the eccentricity of their orbit as a function of time. So migration starts, planets go in. Sometimes there is some migration reversal, but this is a local phenomenon that eventually stops. So planets go in until they reach the inner edge of the disk. There should be an inner edge in the disk because at some point the magnetic stresses overcome the viscous stresses in the disk, and so the disk should be truncated. So planets migrate until they come to the inner edge of the disk where they stop, but then new planets come in, and so they accumulate close to the inner edge, and this at some point brings too many planets, and this system is not stable, so planets have to merge. And so in the end, we have a handful of planets of masses, typically of several Earth masses, typical of super Earths to mini Neptunes that cluster close to what is the inner edge of the disk. And this may reproduce the close-in super Earth systems that we see around, as I said, about 50% of the stars. But of course, this process cannot go on everywhere because not all stars have close-in super Earths, and our solar system don't. So what else can happen? Well, let's imagine, so let's start from a system like before, so significant planet only forming beyond the snow line within the gas disk lifetime. But let's introduce a little change. Let's introduce that by chance, the innermost of these protoplanets beyond the snow line becomes big enough to start accrete gas. And so it becomes a giant planet, more massive than the others because it has accreted gas, whereas the others are only icy cores. And the giant planet migrates inwards, still towards the sun, the star, but more slowly than small planets because it opens a gap and has to change the structure of the gap. It's called different migration mode. So this is what happens. The planet migrates inwards more slowly. The other planets would like to migrate much faster and become close-in super Earths like we've seen in the previous simulations, but there is the giant planet on their way. And it's difficult, not impossible, but difficult for a planet to migrate across the giant planet. It's more likely to be confined beyond the giant planet, in a resonance with the giant planet, and stay there. It's like when you're driving on the mountain road and you have a truck in front of you. Your car is faster than the truck, but overtaking the truck is difficult. And most likely you stay beyond the truck, behind the truck. And so these planets are collected in resonances with the giant planets. And if there are too many, there is not enough room in the resonances, so they merge with each other, so they can grow. We have some planets growing up to 20 Earth masses in this simulation, but they stay behind the giant planet. So we have no close-in super Earths in the end. So this starts to look a little bit like our solar system. We have a giant planet, icy planets beyond it, like super Neptune here or mini Neptunes here, and no close-in super Earths. But it's not the solar system, clearly, because the giant planet, Jupiter, is not a 1.5 AU, it's a 5 AU. And if Jupiter had come down to 1 AU, well, of course, the entire terrestrial planet region would have been destabilized. So what could have happened in our solar system? Well, it could have happened that by chance, not only the innermost of these big icy planets forming beyond the snow line accreted gas and became Jupiter, but also the second one became big enough to accrete gas and grow to the mass of a giant planet and to become Saturn. And hydrodynamical simulations show that if you have both Jupiter and Saturn, there is a gravitational game of these two planets with the gas that really blocks their migration towards the star. If anything, the planets can migrate outwards. And this is probably the reason why Jupiter remained far from the star, or even reversed migration and went back to 5 AU. So let's imagine, for simplicity, in order not to introduce too many knobs, that once Jupiter and Saturn form, they don't migrate. And then this is what happens. The other protoplanets tend to migrate in, but now they don't have one track to overtake on a mountain road. They have two tracks to overtake on a mountain road. It's impossible. So they all stay behind, they all park in resonances, and because there is not enough room for everybody, they can collide and grow. And if you wait a bit, you will see that this 4-planet system, eventually, after an instability, will reduce to a 2-planet system. And the masses of the remaining planets will match the masses of Uranus and Neptune. So in this case, we have a giant planets that stay far out. We have Uranus and Neptune forming on a longer time scale, and the terrestrial planetary region is not affected by giant planet migration. So these small silicate planets, initially of mass of Mars, have time to keep colliding over hundreds of millions of years and form the Earth and Venus. By the way, I think this is a good model for the formation of Uranus and Neptune. It's unlikely that Uranus and Neptune form directly by pebble accretion. Sorry, I click the animation again. And the reason is that Uranus and Neptune have a spin axis which is very tilted. And planets that form by pebble accretion should have the spin axis perfectly vertical. And while Saturn, you say, has a spin axis which is not vertical, but there are dynamical mechanisms to tilt Saturns by spin orbit resonances. Recent paper, for instance, in Nature Astronomy by Melen Senfest, very interesting. But for Uranus and Neptune, no soft mechanism, spin orbit resonance, has ever been discovered. So the tilt of Uranus and Neptune is most likely due to impacts. And of course, this means that these planets did not grow solely by pebble accretion, because certainly not a pebble that is able to tilt Uranus or Neptune. So you need giant impacts of Uranus and Neptune with protoplanets of several Earth masses. And the kind of dynamics we have seen builds Uranus and Neptune by giant impacts of super Earths, actually, with masses of 3 to 5 Earth masses. So in the growth mode, we have enough giant impacts to understand the random orientation of the spin axis of Uranus and Neptune. So I think really the obliquity of Uranus and Neptune is a smoking gun that, although pebble accretion is probably very important in the outer solar system, not in the inner solar system because of the Jupiter barrier, but in the outer solar system, pebble accretion was not enough to form Uranus and Neptune, and we need a phase of giant impacts, probably assisted by the presence of Jupiter and Saturn, creating this barrier against migration to form these planets. Okay, all of this I described, and I should accelerate a little bit, concerns what happens during the protoplanetary disk phase. At some point after a few millions of years, the gas is photoevaporated and goes away, and the planets remain alone with planetesimals possibly around the star. So is the evolution finished? Not at all. We see evidences in extrasolar planetary systems that after the gas is removed, most planetary systems become unstable at some point or another. The evidence is twofold. If you look at super Earth, close-in super Earth systems, and we look at the typical separation in orbital periods between planets, we see a distribution which is not what we expect from the simulations. The simulations of migrating planets that go to the inner edge of the disk and park there lead to all planets being locked in mean-motion resonances. So if you do an histogram of all the planetary systems producing simulations, reproducing the cumulative distribution of the period ratio between adjacent planets, you see a staircase where each step occurs at an integer period ratio, 4 to 3, 3 to 2, 2 to 1, 5 to 4. This is because all planets are in resonances. And we do see some planetary systems in resonance, TRAPPIST, for instance, right? And but they are very few. If you look at the overall cumulative distribution of period ratio between adjacent planets discovered, for instance, by Kepler, what you see is this green curve, is this gray curve. And so first, it's much more distended that this green and red curves coming from migration simulations, which means that the systems are much less compact because the period ratios can be much bigger than 2. And also you don't see any staircase because the resonance systems are rare. So what does this mean? That migration does not exist? It's really difficult to say that migration doesn't exist. It would be a violation of physical principle. But instead, this suggests that planetary systems, after the end of migration, after being locked in resonances and after disk disappearance, become unstable. And if you take these resonance chains and you destabilize them a little bit, the orbital period distribution becomes this one. And we have 2 different experiments in this paper by Isidoro et al. Leading to this red distribution or blue distribution that are so similar to the gray distribution to be a good match. So this suggests that most super Earth systems become unstable after migration and disappearance of the protoplanetary disk. And probably just a few % of the super Earth systems remain stable and appear like resonance chains today, like the TRAPPIST resonance chain. And if we look at the giant planets, as I said before, we have these huge eccentricities. Giant planets should form like all planets from a disk, so should form from a circular orbit. So how can you get an eccentric orbit in the end? So there's been several studies trying to excite giant planet eccentricities by planet disk interactions. They don't really work unless the planet is extremely massive. So they don't reproduce what we see in the mass eccentricity diagram. Instead, the instabilities can do the job. If you assume that when a system produces a giant planet, it actually produces several, say 3, then initially everything is circular, embedded in the disk of gas. Then this gas disappears. The planets are not embedded in the disk of gas anymore. So the gas is not damping the orbital eccentricities of the planets. And then if you wait enough, many of these 3 giant planet systems become unstable. And you will see in a second what happens. So when the system becomes unstable, the planets start to scatter off each other. Some giant planets are ejected, others are thrown very far out, so they can become distant planets like those observed in direct imaging surveys. And the innermost planets becomes a warm Jupiter here, for instance, with a semi-major axis of 2AU and an eccentricity of oscillating between 0.2 and 0.4. And indeed, if one does many of these simulations, as for instance Sean Raymond did, but many others as well, one can reproduce the eccentricity distribution of giant planets really well. So so instability seems to be the rule for both super Earth systems and giant planet systems. And we think that in our solar system, also a giant planet instability occurred. And why do we think so? Because if giant planets formed in the disk of gas, so should have migrated. I said Jupiter and Saturn don't migrate, they lock inside themselves in resonance and stop their migration. All the protoplanets behind migrate in resonance with Saturn, collide and form Uranus and Neptune. So at the end of the simulations I showed you before, the one I claimed that reproduces Uranus and Neptune, this is the distribution of the giant planets. They are all in resonance with each other and very close to each other. The most distant planet, Neptune, is 12 AU. Okay, so this is very different from the configuration of the giant planets today, because they're much more separated with Uranus and Neptune at 20 and 30 AU, and there are no resonant relationships between the planets, among the planets themselves. So 2 things are possible. Either, again, we didn't understand migration of the planets, formation of Uranus and Neptune, everything I told you before is not true, or there is a process that is able to transport the planets from the primordial configuration acquired during the gas disk phase to their current configuration. And we claim, and this is the essence of the NIS model, that this process is a dynamical instability. So what we do now in the most modern versions of the NIS model, we take the orbits of the giant planet as they come out of the hydrodynamical simulations, we remove the gas and we add the planetesimal disk extended from a few AU beyond Neptune to about 30 AU for a total mass of about 20 to 30 Earth masses, and we let the computers work. And what we see is that as time passes, there is some interactions among the giant planets, between the giant planets and the trans-Neptunian disk. And this shake the orbits of the planet a little bit. until an instability occurs. When this instability occurs depends on this gap. If the planetesimal disk is very close to the giant planets, the instability occurs very quickly. If it's far, like in this example, to give me some time to talk, now the instability is late. It happens 800 million years after the beginning of the simulation in this case. But it doesn't matter the result. It does not depend very much on the timing of the instability. And as you can see, the instability spreads the planets, tosses Uranus and Neptune out directly into the planetesimal disk, disperse the disk. The dispersal of the disk by dynamical friction puts Uranus and Neptune on circular orbits as they are observed, and only Jupiter and Saturn remain mildly eccentric. So these really look like the real orbits of the giant planets. And so we think that, we claim that the solar system underwent this instability, and this explains the current structure of the outer solar system. You would wonder, I mean, you may have noticed a little incoherence, right? I said before that the giant planet instabilities can produce the large eccentricities of the extrasolar giant planets. I told you now that the solar system went through a giant planet instability, but I also told you that all planets, including Jupiter and Saturn, have a small eccentricity, less than 0.1. So where is the inconsistency? Well, again, it's another trick of chaos. When the instability occurs, planets encounter with each other, and it really depends on the sequence of encounters that the planets experience. So when we ran the simulations of the NIS model, we get good solar systems only in a fraction of the cases, typically 5–10%. And the rest of the cases, the chain of encounters happens differently, and we get different planetary systems. A big divide is whether Jupiter has encounters with Saturn or not, or only has encounters with Uranus and Neptune. So if by chance Jupiter doesn't have any encounters with Saturn, at the end, Jupiter's orbit has a small eccentricity, like this one, similar to the one of the real Jupiter. But in the cases, in the simulations where by chance Jupiter does have a close encounter with Saturn, then the excitation is much bigger, because of course Saturn is a big brother. And so at the end, typically Uranus and Neptune are ejected, Saturn is tossed far out on a distant orbit, and Jupiter lands on an orbit with an eccentricity typically of 0.4, which compares well with the eccentricities of the warm Jupiter with semi-major axes about 3 to 5 AU, which are here illustrated by these red dots, where the size of the dot is proportional to the radius of the planet, cubic root of the mass of the planet. So indeed, again, depending on which kind of encounters the planetary system experiences, one can have a very mild planetary system in the end with all orbits almost circular, or a much more excited system where even the giant planets have eccentric orbits. And if you remember the simulations I showed you before, this one, when the giant planets become very eccentric, the terrestrial planets that are here forming tends to become overexcited or even be tossed into the sun. So the fact that we do exist here on a circular Earth with a stable climate is really due to the fact that luckily Jupiter did not encounter Saturn, and so did not become a guy like this one. So this drives to my conclusions. Oops. To summarize, even it's an hour, sorry to be a little bit long. So planet formation and evolution are the same everywhere. Of course, physics is the same everywhere. So in terms of growth, the main processes are collisions and pebble accretion. But then we have seen that as soon as planets become sizable, they start to migrate. And migration is also a genetic process. And also generically, once the gas goes away, planets, when they form, they don't know they have to remain stable for billions of years. So there is no reason that the formation process naturally parks the planets on stable orbits. How could the planets know that forming in a few million years, that they need to be in a configuration stable on billions of years? So it's natural that on a long time scales, the planets eventually become unstable and the system reshuffles and changes of orbital structure. Migration in particular, but also these instabilities, introduce a lot of variability in the final outcomes. There can be already in the initial conditions in the structure of the protoplanetary disks, as Alma is showing. But migration and instabilities certainly do a lot to explain the great diversity of the planetary systems in the end, because this introduced a chaotic evolution, and chaotic evolution is very sensitive on initial conditions and environmental parameters. And I gave you a few examples on that. So the structure of the solar system, which I remind you is very atypical, having a Jupiter far from the star on a circular orbit, at most exists around 1% of the stars only. And this is due, according to our understanding, which is certainly not perfect, to 3 fortuitous events. So the first event is that of the big planets that were forming by pebble accretion beyond the snow line, the biggest became big enough to start gas accretion and become a giant planet and became Jupiter. And this prevented all the other icy planets from migrating into the inner solar system, crossing the terrestrial planet zone and becoming close-in super Earths. Then we have been lucky because also the second one started to accrete gas and became Saturn. And Saturn was instrumental in preventing a large range migration of Jupiter. Without Saturn, Jupiter would have become a warm Jupiter, probably around 1 to AU, and causing problems to the formation of the Earths. But Saturn blocked the migration of Jupiter or even pulled Jupiter back. And this left a safe haven in the inner solar system where the terrestrial planets could form on a time scale of hundreds of millions of years. And the last chance is that at the time the giant planets became unstable, like most giant planet systems, Jupiter and Saturn did not encounter closely each other. And so the excitation was mild, and Jupiter remained on a quasi-circular orbit, and this allowed the terrestrial planet to prosper and keep growing and remain there. So at the current state of understanding, we are not really able to put a probability around each of these events and then do the product of the probability to get the combined probability. So I'm not able to answer the last overarching question. So how frequent should be a planetary system like ours? But you understand that if the structure of our solar system has to come not from 1 but 3 fortuitous events, while it should not be, the probability should not be large. So I think our planetary system is actually really an oddity among extrasolar planetary systems, well below the 1%, which is the observational characterization of the Sun-Jupiter systems, but future observations will tell. And of course, our planetary system has allowed the formation of a habitable planet. So if some specificities of the structure of the solar system are instrumental to allow the formation of a habitable planet, then of course it's not surprising that our solar planet just represents a minority of planetary systems, because we have to live on a habitable planet. And so if these conditions are needed, that's why we are here. So I will stop and I will take your questions. Thank you very much for your attention.
Thank you very much, Morbi, for a wonderful talk. And of course, that all ties into the question of how likely a second Earth is. There are already lots of questions in the chat. There are actually 2 chances of you to post questions. Either you write in the chat and I will read the question to Morbi and he will answer them, or you raise your hand and then Billy will give you the microphone and you can post your question yourself. But at the moment, we seem to be having a problem with Morbi. We seem to have lost him. Morbi, are you still there? This is what I feared might happen one of these days, that the Zoom would probably lose connection with the speaker. Fortunately, here at the end, but oh, here he is. Okay.
Hello. Sorry,
okay.
I
we lost you, but here you're back.
Yeah, when did you lose me?
Well, at the end of your talk. I mean,
because I heard a thank you from you, and then everything froze out. Okay.
Yeah. I mean, actually, your image was frozen, but we could still hear you, and now we can see you speak.
I'm sorry.
Okay, no
okay.
problem. I think it's.
Yeah.
So I have to. Okay, where are? Yeah. So again, I hope you heard me saying that we have two ways of posing questions. One you write in the chat, and I will read it to Morby,
Yes.
or you raise your hand, and Willie will then give you the microphone. We'll switch back and forth between the two. So here is already a first question that was posed quite early on. Are the masses in the census plot actual masses or just lower limits?
So in the diagrams I showed, these were coming from radial velocity surveys. So it's a lower limit because there is always a sinus I. But for statistical purposes, you know, the most probable sinus I is a number close to unity. So should not change the general considerations I made.
Okay, Stefan Niculescu asks, how does the revised Nice model explain the location of the asteroid belt?
Well, the asteroid belt is interior to Jupiter, so it's not really the Nice model is, well, sometimes the names are given for different things. The Nice model is really about this phase of instability of the giant planets. So the instability of the giant planets excites the eccentricities and inclinations of the asteroids in the asteroid belt. So what we see today, which are this big dispersion of eccentricities from 0 to 0.3 and inclinations up to 40 degrees, can actually come from mostly from the giant planet instability. The migration of Jupiter and the migration of Jupiter, of course, affected the asteroid belt. So it's not clear if Jupiter migrated inwards through the asteroid belt and then outward again. In this case, the asteroid belt was destabilized, depleted, and partially repopulated, or if Saturn blocked Jupiter's migration before really coming into the asteroid belt. We don't know. Both models exist. So if Jupiter did not go through the asteroid belt, probably the asteroid belt did not contain much mass from the very beginning. If instead Jupiter migrated through the asteroid belt, then the asteroid belt initially contained much more mass, and the migration of Jupiter was instrumental in depleting most of the mass of the asteroid belt. Some mass is also lost during the giant planet instability, but typically only a factor of 4 to 5, and only some extreme giant instability evolutions deplete the asteroid belt by more than 90%.
Okay, I read one more question before I go over to the raised hands. So Neil Turner asks, thanks for this clear talk. Does it matter whether the protostellar disk's gas is removed starting from the inside or from the outside?
Well, if not too much, I would say, because according to the photoevaporation models, everything happens very quickly. So the evaporation from the inside out helps a little bit in explaining the warm Jupiters. According to photoevaporation models, the disk starts to be depleted by photoevaporation at a specific radius around 1 AU, where you receive most of the energy from the star, but you're not too close to the star, so you can escape from the potential well. And this indentation of the disk due to photoevaporation cuts the disk in two. And of course, if the giant planet has not migrated below 1 AU by the time this happens, there is a gap forming there, and the planet cannot migrate through this gap. So it has been proposed already several years ago by Richard Alexander and Ilaria Pascucci that this can explain this inner edge. So photoevaporation inside out from 1 AU can explain the inner edge of the warm Jupiter population. As we have seen, there is the warm Jupiter population, then there is a mid region where there are very few giant planets, and then we have another pile up due to the hot Jupiters. So photoevaporation from inside out can explain that. If photoevaporation was only outside in, then of course that explanation would fail, and would be a little bit surprising that there is a deficit of giant planets in between hot Jupiters and 1 AU.
Okay, I think William Wall was the first to raise his hand. So Willie, can you give William the mic?
Hi, yeah, can you hear me clearly?
Yeah, very clear.
Okay, great. Yeah, I mean, this whole field is, with all the various physical processes, is just fascinating. But and I like the way you explained it in your talk. explain these processes. But I'm wondering now, I mean, in your that plot, I mentioned it in the question I typed in, the plot of the census of exoplanets. You have that sample of exoplanets, and now you said that we made a mistake in the past by assuming our solar system is typical of other exoplanetary systems, or would be the same throughout the galaxy. But maybe we're making a similar mistake, because now we're looking at a sample, and if you look at that sample, it doesn't look typical either, because the major axes are all less than 1, or almost all less than 1, and so that's probably not typical either. And what I'm wondering is, where are these exoplanetary systems we observe? Are they young, and over time would they evolve to look like the solar system? Maybe.
No, the planetary system we look at are not young, are mature main sequence around main sequence stars. And once you have a hot Jupiter or close-in super Earths, there is no possible evolution to bring the system back to super Earths, to the solar system structure. You are right that there is a huge region of parameter space that, of course, observers have not sampled. And of course, all bets are off on what we will discover there. And but again, I stress my point: 70% of the stars have planets that we don't have here. So 70% of the stars have systems which are different from our own. Maybe 30% have systems similar to our own, but 70% are different. But then you can focus on Jupiter, because Jupiter is observable around other stars. Now, I mean, you can not say the Earth is rare, because we cannot discover the Earth around another star with current technology, but Jupiter we can. And so the surveys show that the Jupiter at about 4-5 AU on a circular orbit, which are characteristics that are sort of needed for the Earth, because if the Jupiter were eccentric, the Earth would be very eccentric, and then you can imagine the seasonal cycle, right? If the Earth going from perihelion to aphelion. So you want that if you have a giant planet, it has to be circular, and you want that it stays out of your zone, because otherwise it disturbs the terrestrial planets in its growth. So if you focus on stars that have Jupiter-like planets, so 4-5 AU away, circular orbit, and indeed we can observe those, that's 1% of the stars that have been explored. So if you just restrict Jupiter to the Sun-Jupiter couple, neglecting all other planets and their properties, you find the solar system around 1% of the stars of the galaxy.
Okay, Jim Head is next. Hi, Jim.
Hi. You're muted still.
Got it.
Yeah.
Spectacular talk, Morbidelli. Really spectacular. I have a parochial kind of question. Do your simulations in any way give us insight into the slow retrograde motion of Venus and the differences between Venus and Earth? Can you give us something to work on here?
Yeah, congratulations for the approval of the Venus missions. Heard yesterday. So, well, the terrestrial planets are believed to have formed from these small planetary embryos, silicate planetary embryos that could not grow much within the gas in the protoplanetary disk. So they were sort of Mars mass. And after the disappearance of the gas, these embryos collided with each other and growing Earth and Venus. This is model goes back to George Weatherly, but essentially is still up and correct. So through this sequence of impacts, of course, this final spin of the planet should be random, a little bit like that of Uranus and Neptune. And and it's enough that the final spin of Venus was somewhat retrograde, and then tides would bring it down to 180 degrees obliquity. In principle, the fact that the Venus doesn't have a moon can give also a chaotic obliquity to a prograde Venus. So there was an old paper by Jacques Lascar showing that a prograde Venus in principle can have a chaotic variations of its obliquity, bringing it to 90 degrees. And then from 90 degrees, tides can bring it to 180 degrees. But I think, well, that study was interesting, but I think really the build-up of Earth and Venus and not Mars and Mercury through giant impacts suggests that their spin obliquities was random. Finally, the Earth had 23. maybe Venus had 98, like Uranus, or 120. I don't know. Any value bigger than 90 would become 180 by tides.
All right, I take one more and then go back to the chat. So Bana Fuang, but I note that Morby, you have an ISI pen in your hand. Very good.
Yes, thank
it's
you.
true, and I didn't do it on purpose. I just play with my pens when I speak, and I picked one. I have one from the ERC as well, but just okay, go ahead, Bernard.
Oh, yes, so yes, a great talk. I have some question about the very early time, like the first million years, where the sun and the stars, they are in their very active tertiary phase. We have also indication of magnetospheric accretion. So a lot of mass from the inner planetary disk is being lost back into the star. So in the transition phase, like post-tertiary, what is happening to the inner disk? And so is there a role of some of these magnetic processes also to, there was a theory also of magnetic or Jupiter migration. So what is the role of the sun or the star's magnetic field in influencing what happens in the inner planetary disk?
Sure. So I'm not really an expert on this, but certainly it's expected that the magnetic field on the star truncates the disk. So the disk is not extended all the way to the star, but at some point is truncated, and the dynamics of gas accretion to the star changes. Outside, it's gas spreading due to some viscosity or removal of angular momentum in winds or whatever, but then it's funneled in magnetic channels and so on. So as a result of this truncation, planet migration eventually stops. And this, I think, it's not important for the solar system, but because we don't have any planets as close, but in systems where planets became big enough to migrate, eventually they stopped. And so this is why we have this accumulation of short period planets, both giant planets and super Earths around so many stars. So that's already an important result. It was.
So you don't expect some of them to be swallowed back into the central star?
By the magnetic interaction, I don't think so, but some planets can be swallowed by tides. I mean, the tidal evolution on long term can still drift planets towards the star, and if they are close enough, they can eventually fall onto the star. That's some planets can be removed, like Phobos will fall on Mars.
So we don't expect, for instance, that there could have been a hot Jupiter in our own solar system?
Well, I mean, Doug Lin, and of course it's Doug Lin, so has great ideas. He proposed that maybe as a solution of the migration problem, that planets form and migrate and fall on the star, and what we see are just the last of the Mohicans, right? Yeah. So Jupiter would not be the first Jupiter forming in the solar system, and others existed before and migrating into the sun. I don't believe it too much, because for two reasons. First, again, the fact that we see this pile up of planets close to the stars suggests that there is this truncation of the disk. So it's not easy to migrate all the way into the star. You need to migrate to the inner edge of the disk and then be close enough to be swallowed by tides on a longer time scale. And a migration, large migration, wide migration of a Jupiter planet from beyond the snow line through the terrestrial planet region to the inner edge of the disk would have strongly depleted the terrestrial planet region at the point of preventing terrestrial planets formation, I think. And so we don't see any evidence of anything big really migrating through the terrestrial planet region.
Okay, yes, thank you.
So I think Jupiter was the first of the innermost of the big planets forming beyond the snow line, and by accreting this gas, slowed enough its migration, and then was helped by Saturn, so that it really never came down to 1 AU.
We have so many more questions, so I'm now taking 3 more from the chat and then go back to the raised hands. So Vitaly Chicha, as I understand nowadays, no one system with the same structure as our solar system and Earth-like planet on a 1 AU around a G star.
Yes, but this is a bias. Okay. So because we have, as I said, the only planet we can observe with our technology around another star is Jupiter. And 1% of solar type stars have a Jupiter more or less like our own. Okay, 1%. But the other planets we cannot see. So we don't know if this is every time. The question is, does a system that has a Jupiter like our Jupiter always have the rest of the planets like our planetary system? I'm not sure. And if yes, then maybe the Earth should exist around 1% of the stars. But I'm not sure that having Jupiter on a circular orbit is enough to make an Earth at all. For instance, imagine the giant planets form more slowly. So that means that its barrier against the drift of dust from the outer disk to the inner disk becomes effective at a later time. So the inner planetary system, instead of seeing basically no drift of outer solar system material into the inner solar system, sees tens of Earth masses of dust going through. Then the Earth would not be an Earth, would become a super Earth within the lifetime of the disk and would migrate. And even if it started to form in the habitable zone, it would end inward of the habitable zone, so too hot to be habitable. So I really don't know. I don't think that just having a Jupiter on a 5AU orbit, circular 5AU orbit, is enough to guarantee that there is an Earth. Future will tell.
Veronique Dehan asked, first, very nice talk, Alessandro. What about the Trojans in the model? Can you elaborate on these?
Yeah. The Trojans are, these are planetesimals of cometary nature, actually, that share the orbit of Jupiter and the orbit of Neptune. And they are very well explained due by the giant planet instability. So the giant planet instability disperses the trans-Neptunian disk of planetesimals by injecting there Uranus and Neptune. So the trans-Neptunian disk planetesimal get dispersed. They go everywhere. Some are transported into the current Kuiper belt. Some are trapped into the Oort cloud. Some go around the giant planets and are removed. But because the giant planets are moving, thanks to their mutual encounters, some of these planetesimals can find themselves on the orbits of a planet, on a stable island on the orbit of a planet. And indeed, the simulations have been done by David Nesvorny, was the leader of these simulations, reproduced the orbital distribution and the total number of Trojans at both Jupiter and Neptune really well. So the Trojans are trans-Neptunian objects captured during the instability. And I think this was a driver to select the Lucy mission by NASA, because actually it's a way to visit Kuiper belt objects much closer and cheaper to us than going all the way to the Kuiper belt.
Okay, Sadeep Gogate asked, would you say that with regards to the Nice model, the interaction of Jupiter and Saturn might have consequences on the TNOs and perhaps even on planet IX if it so exists?
So yeah, the Nice model, one of the smoking gun of the Nice model is not only that it explains the current orbits of the giant planets, starting from a more compact and resonant configuration, such as those we get in migration simulations, but is also to explain the Kuiper belt. And there has been an outstanding body of work throughout the decade by David Nesvorny, who has been able to basically reconstruct all single structure observed in the Kuiper belt. And so we have a very detailed reconstruction of the structure of the Kuiper belt in the framework of the Nice model instability. And indeed now, when people do experiments about the Nice model, typically now there are 2 or 3 reference simulations that are considered because they really reproduce the Kuiper belt very well. For Planet 9, Planet 9 is not related to the Nice model. So you may, the most recent version of the Nice model actually starts from a giant planet systems that have 5 planets, Jupiter, Saturn, and 3 planets like Uranus and Neptune. We can form this configuration as well during the migration phase, even if the simulation I showed only formed 2 planets. I have others forming 3 planets. And during the giant planet instability, 1 planet is ejected and 2 become Uranus and Neptune. This ejected planet cannot be Planet 9 because in order to be trapped on an orbit like the one needed for Planet 9, if we need a Planet 9, so it's about 1000 AU, the solar system should have been, at the time of the NIS model instability, still embedded in a stellar cluster. The density of the stellar cluster tell you where, at which distance, planet objects scattered by Jupiter and Saturn can be stored. Okay. In the current galactic environment, this location is the Oort cloud, 20,000 AU. So instead, if you want to save a scattered object and in place it at 1000 AU, you need to do it when the solar system is still embedded in a dense, relatively dense stellar cluster. So the ejection and capture of Planet 9 should have occurred earlier than the giant planet instability, presumably during the phase when Uranus and Neptune were building up in this migration, scattering, collisional process that I illustrated in one of the simulations. And if one of these protoplanets, you start from a handful of protoplanets that collide with each other to form Uranus and Neptune. If one is ejected by Jupiter and Saturn, and there is a cluster, it can be trapped at 1000 AU and become Planet 9. But at the time of the giant planet instability, the Oort cloud was built. So the solar system was already out of the cluster. If the giant planet instability had occurred in a cluster, we would not have an Oort cloud today. So the Oort cloud is the smoking gun that the sun was already out of the cluster when the giant planet instability occurred. And then this means that you cannot emplace Planet 9 in its current orbit, putative orbit, during the giant planet instability.
Okay, Mark, I'm switching now to the hands again. So Mark Hofstetter would be next.
Yes, hello. Thank you again for a great talk, as everyone says. I was just wondering if you feel we have a good understanding now of how Uranus and Neptune avoided accreting huge amounts of gas and becoming gas giants.
I would not say that, but you know, if they accrete through this phase of giant impacts, first they should this takes time, and so the gas in the same time is decreasing in mass. Also, giant impacts tend to blow off part of the atmosphere. They heat the planets enormously, which also helps preventing the accretion of the atmosphere. So these are all considerations, issues to be considered, and which might help in understanding why so little gas was accreted. Also, if the disk viscosity was not very high, the accretion of gas is slowed down. So if you can protract the building up of Uranus and Neptune for a few million years through this process of collisions, then probably they don't have the time to accrete much of the gas. But I've never modeled specifically the accretion of gas. I mean, the models that I showed you about planet formation, to be honest, there is no gas accretion on the planet. We just look at the composition of the solid mass. And so we have never considered using a thermal model and if too much gas would have been accreted or not, to be honest with you.
Thank you.
Hans Dieck would be next.
Okay, yeah, thanks for the great talk. A question is that I have, if we detect a Jupiter-like planet that has a distance of a few AUs, which we know by now already a few cases, would you then predict, and that's a test of your theory, that there should also be a Saturn-like planet in these systems?
I don't know if you can say predict. So the existence of a smaller planet like Saturn would certainly help. And by the way, let me stress that the only two giant planets we see embedded in a protoplanetary disk, which are PDS-70b and PDS-70c, have a mass ratio which is comparable to, well, for what we can estimate masses by direct imaging, but of the order of Jupiter and Saturn, and they also seem to be in resonance with each other. And people taking what is seen in the observations and putting them in computer animation. So Clément Baruteau in France, Jean Bay in Carnegie, what they saw is the grand axe. So the planets don't migrate inwards, they're actually migrating outwards, which seems consistent with the distribution of the dust. So this dynamics of Jupiter and Saturn not migrating in is the one that we see at the first giant planets we observe in a protoplanetary disk. So this is promising that this mechanism actually works, but there can be alternatives. You know, the giant planet could have migrated slowly, so maybe it came down to 3 AU and didn't need anybody else to slow it down. Maybe it started further out because it started further out. Maybe the disk was more warmer at the beginning, the snow line was farther out. Maybe there was another planet that retained prevented the planet to migrate, but then there was a giant planet instability, and the planet that blocked the migration of the planet we see now has been ejected, and so now it's not there anymore. So I would not predict that every time we see a giant planet at 3-4 AU, if we look more carefully, we will find its Saturn companion today because of these reasons. But certainly the past presence of a planet, a little bit smaller, half of the mass, a third of the mass, does help in reducing migration.
Okay, thank you.
Okay, Marchand would be next. Oh, it's gone from the list, so I turn to Mike Way. I'm wondering what you think about the recent work putting some doubts on the veracity of the LHB, the late heavy bombardment, meaning whether a late or early giant planet instability is likely.
Yeah, I have no problems on that. I'm actually have even a paper about the early instability. So as I said, I was rushing a little bit at the end because it was really getting too long. The timing of the giant planet instability depends on the gap between the orbital location of Neptune and the inner edge of the planetesimal disk beyond Neptune. And we don't know how big was that. It really depends on how Uranus and Neptune built up by migration and so on. So if this gap is small, the giant planet instability happens very quickly in a few tens of millions of years. And only if this gap is made big, you can have instabilities late. Now, originally, the NIST model was proposed to, the instability was proposed to have occurred late because several experts were arguing that the moon underwent a peak in the bombardment around 3.9 billion years ago, so about 600 million years after planet formation. So people were saying, okay, I mean, the indications for this spike seem robust, but how can you cause a spike in the bombardment? So we proposed, well, if instabilities can occur also late, and we do see the evidence for a late spike, then most likely explanation is that the instability occurred late. But nowadays, with more analysis, in particular the analysis of impacts in not in the whole rock of the moon, but in clasts inside the lunar sample, show that indeed there have been many impacts also before 3.9 billion years, so going beyond the work originally done by the Caltech group, Theira et al. And so this idea of the impact spike 3.9 billion years ago has been slowly disappearing. And if there is no strong evidence for an impact spike 3.9 billion years ago, there is no reason that the giant planet instability occurred so late. It's much more probable that the giant planet instability occurs early than late. You really need to have a specific gap in order to have a late instability. So I'm perfectly fine with a NIST model instability occurring, 50 million years down the road, maybe coeval with the moon forming event. We still need to understand what drove the moon forming event. Maybe it was a giant planet instability. Some people, like Matt Clement, has published a series of papers arguing that the giant planet instability occurred very early, as soon as the gas disappeared, and this may explain why Mars didn't grow big enough. So all these ideas are on the table, and so they are all consistent with the idea that giant planets become unstable and just play on the timing of the instability. More work is needed to really pinpoint the timing of the instability.
Okay, I think I take a few more, and then we'll need to close this. Unfortunately, we have so many more in the chat, but there's only a finite time that we should. So Joseph Trigo Rodriguez asks, so migration inwards of the gas giants was followed by outwards migration of the ice giants. How many percent of the TNO-like population of bodies could have gone inwards? Excellent talk.
Okay, so during the ice giants are tossed, it's not a migration, it's really scattering out. It's an impulse out. This disperses the protoplanetary disk. So of this protoplanetary disk, what happened? So we estimated about 1 in 1,000 got stored in the Kuiper belt. About 5% got stored in the Oort cloud. 1% got stored in the scattered disk. All the fraction being trapped as Trojans is 10 to minus 6 or 10 to minus 7, I don't remember. It's very small. And all the others have been ejected. But by being ejected, that means going through the giant planet's orbit, being scattered for a while before being ejected. So like comets. And like comets, they could have passed through the inner solar system for a while before being ejected. Some have been even trapped in the asteroid belt. We think the D-type asteroids we see in the asteroid belt are probably objects trapped into the asteroid belt. But most of the D-type asteroids are Trojans, right? Not in the main belt. So I hope this answers the question.
Okay, Luke, does the randomness in the chaotic scattering of planetesimals by migrating giant planets place a theoretical limit on how well we could ever hope to reconstruct formation scenarios for planetary systems, not just
That's a very good question, and almost philosophical, you know, because and yeah, it concerns everything, any system affected by chaos. So the answer is yes and no. So the system is not deterministic. So you cannot do a simulation and say, this must be the correct simulation. It's like the weather, you know, you can predict the weather a few days from now, but not exactly what the weather will be in a month. And you cannot reconstruct the weather that was 1 year ago at your place. But what is possible is to explore the portfolio of possibilities of possible chaotic evolutions. This is possible because chaos doesn't mean that everything is possible. Chaos means that there is a wide range of possibilities and they are very sensitive on the initial conditions and the parameters, but not everything is possible. So you can simulate your systems, and you can, if you do enough simulations with what we do, for instance, with the NIST model, you can make thousands of realizations. Okay, this gives you a sense of the statistical distributions, probability distribution of the outcomes. And then you have to compare with your constraints. So you have to compare with what you have. If you know the Kuiper belt and its structure, you can say, okay, all this set of simulations clearly show a possible evolution that didn't happen because the Kuiper belt would result completely different. And so we'll focus on this subset. So this looks like quantum mechanics. You know, you have the spin of the electron, you don't know, but once you measure it, you know, and then you know what is the state of the other electrons that you have not measured. It's the same thing. So chaos by itself kills determinism, but you can work statistically if your system evolves chaotically, and then helping yourself with constraints, you can start to cut down branches and narrow down the realm of possibilities up to some limit. And then there is a realm of possible evolutions that you cannot discriminate until you have more data, more discriminant data.
Okay, Bill McKinnon, wonderful talk, Morby. If you reconnect, can you comment on the possibility of 3 or more ice giants emerging after nebula dispersal? You argue that Uranus and Neptune most likely emerged alone.
No, yeah, sorry. This is I showed the simulation which leads to the formation of Uranus and Neptune, only 2 planets. but there are other simulations in the same paper. I can send one to you, because now if you start to search for the animation, it will take too long. That, for instance, forms free. Okay. Now, again, and this joins smoothly with the previous question, how can we know if there were 2 planets or 3 planets? Well, statistically. So a huge work done by David Nesvorny, took part also, but David was the leader, started to look at statistical outcomes of the giant planet instability, starting from a system of 4 planets, Jupiter and Saturn, Uranus and Neptune, or system with 5 planets, Jupiter and Saturn, and 3 planets of Neptune mass, and even 4 planets of Neptune mass. And of course, nobody is arguing that there was an extra Jupiter or an extra Saturn, because they would not be removed. And he found that the probability to reconstruct the current planetary orbits are much bigger if one starts with 3 ice giants, so 3 planets like Neptune, rather than 2. And the reason is that you can spare one. The instability can be a little bit more violent and lead to the ejection of a planet. If instead you start with 4 planets and you want to keep 4 planets, then instability has to be really mild. And then typically you have issues with the eccentricity of Jupiter, which is too small. So the argument of the argument brought by David Nesvorny is that there is a significant probability advantage in supposing that there were 3 ice giants in the beginning. Instead, you don't gain anything in supposing that there were 4. So 4 is an extra assumption, but the solar system is producing the solar system at the end, it does not become more probable. So Occam's razor would lead to reject the idea there were 4 ice giants, but this probability evaluation supports the idea that indeed there were 3 ice giants, even if the final proof we will never have.
All right, we have so many more, and I think we can't exhaust them tonight. And I also would like to have my IT manager give a chance to go home. There's one that also, I wonder about. What happened to the Grand Tack? You didn't mention the Grand Tack at all.
Yeah. So, I mean, it's an hour talk and it went too long, so I had to do my choices. And so the Grand Tack, and I didn't talk specifically on the subtleties of terrestrial planet formation. So a puzzle of terrestrial planet formation is that we have 2 major planets, Earth and Venus, and 2 minor planets, Mars and Mercury, which stayed at the level of the embryos. And so the question is why these embryos remained embryos and did not accrete with other embryos to become more massive planets. So it seems the answer is that there was little mass around the orbit of Mars and around the orbit of Mercury. And the question is why. So the Grand Tack proposed that Jupiter migrated towards the star, the sun, until Saturn formed, and then the planets started to migrate back out. And if the timing had been correct and so on, and the Jupiter had come down to 2 AU, 1.5 AU before being brought back by Saturn, this explains the depletion of the asteroid belt, the depletion of Mars feeding zone, and leaves Mars small. This is a possibility. It requires really fine-tuning the migration of the giant planets, but it's a possibility. But other ideas have emerged. One idea I mentioned before, if the giant planet instability had occurred very quickly just after gas removal and had been particularly violent, although still compatible with the giant planet's orbit at the end, then the material could have been removed from the asteroid belt and Mars zone by the giant planet instability itself. This is Matt Clement's model. And another possibility is that the initial distribution of planetesimals was not smooth at all. And actually the streaming instability, formation of planetesimals by streaming instability in some sense supports this. In order to create this streaming instability, dust has to pile up in some rings. So the first wave of planetesimal formation is uneven. And certainly many planetesimals form around the snow line. Probably many planetesimals form around the silicate sublimation line. Probably not many form in the asteroid belt and Mars region. So maybe this depletion just comes from the primordial radial distribution of the planetesimal masses. And Joanna Drawkowska, for instance, made this point in 2016, proposed this in 2016. So there are alternative scenarios really to explain the small mass of Mars. I would say there is no smoking gun in favor of the grand tack. It's pretty sure that Saturn helped Jupiter from not coming permanently to 1 AU, but did it really come down to 2 AU before backing out? Honestly, I'm not sure. I cannot claim, nobody can say to be sure. So in a talk like this, I prefer to talk about what we are more confident about, and also extrasolar planetary systems and so on. So the grand tack is still a model on the table, but it's not a unique explanation of the solar system structure.
Okay, thank you very, very much, Morby, for this fascinating talk. And we should thank Saturn, for
we should
have this talk.
Absolutely, my favorite planet.
Thank you very much, the audience. There's still about 100 people in
wow, thanks a lot
to you. And we had at peak, we had 275, I think.
Wow.
So, very, very successful. Thank you very much. Have a good evening. Next week,
too.
Have a talk on the merger history of the Milky Way and what we learned from Gaia, on the Gaia mission. So see you again next week. Joachim Wamskans will be chairing next week. And again, have a good day. Thank you very much. And bye-bye.
Thanks to you for the attention and the invitation. Bye-bye.